Okay, so good morning from California. And I'm gonna just give you a brief introduction to NDM in the aerospace field. I started working in aerospace down at NASA Ames Research Center quite some time ago. And of an interesting note in NDM trivia is that my dissertation was on how pilots make decisions. I looked at how they were making decisions, and I had a set of transcripts from a simulation that they'd run at NASA, and it didn't seem that the pilots were following any of the traditional decision-making modes that were in the literature. And then I found Gary Klein and his recognition primed decision-making model and analyzed the data using that model. And the other thing is that Danny Kahneman was on my dissertation committee. So for that span of time while I was doing my dissertation and getting it approved, they both agreed on the study and the methods. And I think it was Kahneman's, maybe his only NDM dissertation that he ever supervised or was on a committee. So anyway, we've been working for a number of years with NASA. We've moved from aviation into space, and I've been working with my colleague Ute Fischer at the Georgia Institute of Technology, looking at space crew autonomy, communication, and decision-making within the multi-team system. So when you think about the space system, it's a multi-team system, meaning that it's got several teams working together and they are not co-located. So you've got a team in the spacecraft or on the surface of a planet, and you've got a team down on the ground in Earth. And both of these teams are doing their own separate functions, but also they are working together. And so there are a lot of concerns about what's going to happen when you expect this multi-team system to be collaborating. How will that be managed, basically? So remote collaboration and decision-making in a multi-team system during these long duration space missions, and we're talking, they say even if they send a mission to just swing around Mars and come back, it would be about 18 months worth. And they're talking much longer than that with landings and stays on planets or asteroids. So one factor is that communication will be delayed, and the delay will get longer and longer as the spacecraft gets farther from Earth, and it would go up to around, they think about 23 minutes each way is the longest for a trip to Mars. And there are significant problems associated with communication delays, and they seem like they might be trivial and easy to cope with, but we've had feedback from people in space analogs saying, you know, we looked at the voice loops of communications, we looked at the text loops that occurred during scenarios, and we saw afterwards that it was broken 10 ways to Sunday. We were talking past each other. We were taking one response to mean to be a response to a totally different question. You know, it was incredibly broken, and you could only see it when you took the time to analyze it afterwards. And this was a very small communications delay, maybe you know, between 50 seconds and 5 minutes. And even a short delay can really screw up communication significantly. So there's that issue. So the communication is going to be delayed. The crews will need to be autonomous because of this delay and because they're so far away. And autonomous in space talk means something different than autonomous automation. It refers to a change of control from the ground, which is the case now on the International Space Station. The ground pretty much tells the crews their schedule, when they will do what, is their go-to experts for problem solving, for any kind of failures can be fixed from the ground in most cases. But when you get farther from the Earth, there's going to be a lot more autonomy involved, and the crews will be working much more independently. But there are still going to be instances, unexpected events, anomalies, where the crews will be expected to collaborate with the ground. So you've got experts in space and experts on the ground, and subsets of knowledge in both sides. So how do you support shared knowledge and teamwork among all of the members of the space ground multi-team system? And how do you best facilitate decision-making for the expert crew members? How do you help them make good decisions? So when you're examining this from the multi-team perspective, you have to look at, you've got factors on both sides, of course, and you've got experts on both sides with all of their cognitive, personality, motivational states, all that goes into the human, their knowledge, their sense of the team's efficacy, all of theirs on both sides. And then you've got looking at it in the middle at this level of the multi-team system. So you've got the crew having to do their own task scheduling, their own management, their own leadership and decision making, and their own information sharing and reporting, and having control over these things. And this is a change from the way that NASA operates right now. So giving this autonomy to crews and assigning them the responsibilities is different than what is going on. And then you've got this multi-team system level that you have to pay attention to. What is the compatibility and the accuracy of their models on both sides of what the task is, what teamwork involves, how they should be working together, as well as their communication and their interpersonal processes within the multi-team system? How do they transmit the appropriate information to enable expertise on both sides? And how do you guarantee the multi-team system cohesion and effectiveness? Because if the teams don't hold together, if the space ground team doesn't hold together, it could be a pivotal failure point for space missions. And working within all of this, we're looking specifically at communication delays and unexpected events. So we are looking at this from the two different approaches in two different projects. And one of them is support for asynchronous communication. So given you've got this time delay in communication, how do you support effective communication? And we did work in several places looking at this, and including one of the analogs. It's great to study experts in the fields, but it's hard to study experts on Mars or in a long duration mission when there aren't any. So NASA has sets of analogs in which astronauts or astronaut-like people perform simulations. And one of them is called Nemo, and it's under the sea off the Florida Keys. And these are astronauts. And it shares many characteristics of space or isolated, confined environments, in that it's self-contained. You can't go outside without special gear. You're isolated from the world. And it's an isolated and confined environment. And using these analogs, we collect a lot of data. And it's as close as you can get to what would be in space without having to go into space to collect the data. They also use analogs in Antarctica, and submarines have been used as space analogs. So that's how we get our data. And when we did studies in the lab and in these habitats, we found that there were three threats to asynchronous communication. One was the timing. People did not account for how long it was going to take for a message to get to the other side and a response to come back to them. And so they would receive messages and they counted on it as being a response to something that they just sent, when it's impossible that what they just sent could already have gone there and gotten back. Or they would think, come on, I haven't heard back from you. And they keep sending repeat messages because they were worried about what was happening. And this meant it was really hard to keep track of the threads. So if you were waiting for one message to come back to you, the response to a question, you might ask a different question in the meantime, or you might add some more information. And the threads would end up getting totally tangled. So you would get a message and it would say, got that, try it again, or some other thing, and you would have no idea which message they were referring to from the other side, and what's that, and what do they mean, try it again. And it would be very hard to keep track of what went with what. And so we found in one of our studies that people would take a response from one communication to be the solution to another problem, try to apply the right solution to the wrong problem, and get totally tangled and have a lot of trouble recovering. We also found that people would send messages like they do in emails or texts, where they would type a line and send it, and then type another line and send it. And that exacerbated the first two problems, keeping track of the timing and keeping track of the threads. And so transmission efficiency was a problem. So in our research, we are looking at two different ways. We developed communication protocols, which basically are expert cheat sheets telling people how to communicate under time delay when you're conveying information, when you're asking questions, and they address those three issues of timing, thread, and transmission efficiency. So keep track of timing, keep a log, make sure that you've got the timing straight, keep track of the threads, label the threads, make sure that you are not responding with phrases that are not explicit, like got it, or try that, or do that action over again, without being really explicit, and transmitting chunks of information. So chunks that an expert would put together to look at a situation and diagnose it, put those chunks together in a message before you send them. So we developed communication protocols, which now NASA is using for their analogs. They're being refined. And so before any of these participants go into an analog study, they are trained on the communication protocols. And they're also implementing some technological solutions. So for example, they're tracking the timings of messages and making it explicit. Okay, this message came in at this time, and was sent at this time, and this is the earliest time you can get a response to that message. So kind of helping out technologically. And we're also involved in another project that is technological support, which is called Braided Communications. And braided communications is a way of creating a carousel of threaded communications. So it specifically addresses all of the three concerns, but specifically it addresses the concerns of thread and transmission efficiency by keeping similar related messages, instructions, information together in one thread. And also the timing is controlled with relationship to the time delay, because the threads the threads are timed as they go around, so that by the time you are sending your last thread, you're getting the responses to your first thread, and they're all together in one place, so that it's easier to keep track of how the communications are united and how they go together. Our second approach has to do with what happens in autonomous missions, and how do you make sure the multi-team system stays a coherent team system. So how does crew autonomy impact the functioning of the crew mission control multi-team system? And so we're looking at multi-team system members' shared knowledge, their collaboration, their cohesion, the team cohesion, and whether it's intra-crew, intra-component teams. So are you cohesive only within the crew or within MCC, or can we foster cohesion across space? So between the space crew and the mission control, communication and mission performance. What is the impact of autonomy on perceptions of the multi-team system as you get farther away, do you still consider the team on the other side of the world to be part of your team? And how does it impact interactions with mission control? So if you've been gone for a while and there's a significant time delay, how likely are you to call on mission control for help with problems when they could help you, when they've really got more expertise than you do on a particular problem? And how on the other side, how do you respond to requests or demands from mission control when you've been used to controlling how things are done on the spacecraft or on the planet? So how does this multi-team system, how are they going to keep coherence with that? They're very worried if they've got this most sophisticated technology, they can get to a planet, land on a planet, live on a planet, go around a planet. A key component of keeping these missions, making them successful, will be the human, the team component. So how do you ensure that the humans stay together, act as a team, and stay coherent? And what are the leverage points? How can we facilitate this perceptions of multi-team system cohesiveness, and what countermeasures can we introduce? Both of these research projects support a naturalistic decision making in space. We're looking at effective communication and information sharing for situation assessment, structure and organization of information. So how do we facilitate effective communication, because it's going to be essential for making good decisions in space? How do we foster effective collaboration between experts in space and experts on the ground for these anomalies? And one of the things, for example, might be a medical emergency, and you've got a surgeon that's on the ground with the expertise in the particular medical problem that's occurring in space. So how do you ensure effective collaboration between these experts? And down bottom line, how do you ensure effective decision making when you've got a situation that's I don't know if I would call space a naturalistic environment, but it's definitely one that requires this research. And I thank you very much for your attention.